Good morning, guys. Good morning, everyone. Hope this. Hope you are fine. You are fine, and things are okay. Today, our lesson is 12.1 Geometry, Chapter 12, Lesson 1, Lines that intersect circles. In general, Chapter 12 is for circles. We're gonna study all things about circles, and our objective of this lesson is identify tangents, secants, and chords, definitely, of circles. This is the first objective, and the second objective is to use properties of tangents to solve problems. So our objective that students should be able to understand the meanings and implement them practically with calculations and examples, definitely. Our vocabulary here, there are too many. We can see we have interior of a circle, exterior of a circle, chord, secant, tangent of a circle. All of these meanings we're gonna study definitely. What's the meaning of concentric circles, congruent circles, definitely, tangent circles, common tangent, all of these meanings, we're going to study them. As I start with the life example, here we have this photograph that's been taken for 216 miles above the earth. It's going to show us here the curve. You can see this curved shape here on the edge. This bit, you can see this curved shape, which is part of the circle. And it said here that for this altitude it is easy to see the curvature of the horizon, which is the pink I've shaded now. Facts about circles can help us understand details about the earth and planets and whatever. So let us recall how to define a circle. A circle, you can see here is a circle, is a set of all points in a plane that are equidistant. Equidistant means like equal distance from each point. From a given point, which is the center, call the center. So if we have a point and we have points around, all of them are equidistant, they're gonna be for us a circle. So that's what I'm saying. In general, almost it has to be equidistant. Okay, and we can give it a circle C or the symbol circle C. What is the interior of a circle or the exterior of a circle? Imagine that I have here a circle like this one. So inside the circle, the interior of the circle is inside, it's here. Exterior of the circle, it's outside. So any point, even if it's on the circumference of the circle, it's on the circle. Any point, it means in the interior of the circle. Or outside, it means at the exterior of the circle. What is the meaning of a chord? We can see here now, for example, we have a chord. This is a chord AB. Okay. What is the secant? We can see that the secant here is. And a chord is a segment whose endpoint lies on a circle. To be specific, these endpoints, you can see them, B and A. These are the endpoints because it's a line segment, so we can measure it, we can find the measure of this. So any line we can draw millions of lines that intersecting, and their endpoints are on the circumference of the circle. What's the circumference? It is the perimeter of the circle. So what is the secant? The secant that intersects, it means it's coming from outside. Sorry, it's coming from outside, intersecting it and going to, and intersecting it inside and going outside. So it's endless, not only two endpoints, no, it's endless both directions. This is the secant of the circle. So the difference between the secant and the chord has two endpoints. The secant, no, are intersecting but still continuous from both directions. What is the tangent? The tangent is a line in the same plane of the circle, definitely, that intersected at exactly one point. And we can see here, this point here is exactly one point. Exactly one point. So the secant M here, you can see that the secant of a line M here. Okay, what is the point of tangency? It is C. So the point of tangency here is this point. It is the point C. Because of this point of tangency, we have the tangent M. It wouldn't be a tangent for a circle ever, unless there's a point of tangency. So when we say tangent, it means there's a point of tangency. And when we say the opposite, there's a point of tangency, it means there's a tangent. Let us take example number 1. Identify lines and segments that intersect circles. Okay, first of all, let us use one by one. What do we have? Chords. Chords here we can see here. We have JM and we have KM, and both of them there's a segment above them. It means it has to be a segment. So where is JM? We can see that this is a secant JM and a tangent JM and a chord JM. The blue part shaded now, it is a segment. Its endpoint is J and M. Okay, what about KM? Because we can have also a secant, like you can see the secant here. JM is the same letters, but here we have endless. So these parts, in addition to all of the line, the yellow line, is the secant. This is the difference between the chord and the secant. Well, we can see clearly that the chord KM is only a, no, not only, but what I'm saying is only a line segment, only 2 endpoints like K and M. But at the same time, since it's passing through the center, and the center here is L, it means it is a diameter. So we have KM, and I will do it in red. KM is a diameter here, and it is a chord as well, both. So KM is it is the longest chord in the circle is the diameter. To connect between these, the longest chord is the diameter. The difference is every other chord is not passing the center, but the diameter is. So conditionally it is, and it's building to radii or radii in the British language for these, and we can see now. These blue, these are what? Chords in general for the KM as a chord. The red for the diameter because it's passing the center. What about the radii or the radii? The radii we can see here, they are KLM, LJ, and LM. Can you please specify for us? Yes. The radius, it can be this part, half of this one, this is the R, KL, or LK from the center, and LM from another center. And we have another line to the circumference, which one? Which is LJ. So we have another one, which is this one. Is also an R. So we have a 3 radii here, or radii, in this given circle. And from this we have identified all of the requirements the required line or segment in the circle L. As we can see here, there's a circle. Hope that's understood, and that all of these has to be understood well and learned by heart somehow. The meaning of them, I mean, the chord, the secant, the tangent, the diameter, and the radius as a one radius, and the plural radii. Now for the next part, we have this diagram. We are defining things. What's the meaning of two congruent circles? So two circles can be congruent if and only if it means we have two directions. If and only if it means two directions. They have congruent radii. Good, super. It means if two radii are congruent here, they're gonna be two congruent radii. It means this radius AC, if it's congruent to the radius BD, then the circle, all of the circles are gonna be congruent. So mathematically, we can learn it like this. Circle A is congruent to circle B. We can read them by their centers. If AC is congruent to BD, this direction implies the converse of it. If the radii are congruent, if AC is congruent to BD as a radii, then their circles are congruent. This has to be learned by heart well. This is the first postulate, or as a rule or a theorem. What's the meaning of concentric circles? They are coplanar. It means they are in the same plane. Here, it means here coplanar, same plane. They lie on the same plane. Both of the circles with the same center. You can see here the same center. It means this is a center. This is a center for both, for the big circle and the same circle and the small circle. So same plane. The plane considered, this is a plane, for example, and two-dimensional plane. Both of them, they lie on the same paper. If we say a plane is a paper, two-dimensional shape. What about the third one, a coplanar? Two coplanar, it means the same plane. Circles that intersect at exactly one point, they are called tangent circles. Let us focus here. Tangent circle, this is the point of tangency. When they meet in the same, exactly one point. Take the green line here. Here, tangent circle has to be a point of tangency. Where do they meet, the blue and the red circles? With their different centers, because one of them is bigger than the other one, so the radii are different, so they cannot be congruent. But they have one thing in common. What is it? They are touching each other, or in another way we can say they are internally tangent circles, internally from inside here. Internally, this is internally. This is the tangent. What about externally tangent circles? It means the tangent from outside, for both, they are intersecting for both. This is the difference between external and internal tangent circles. Definitely have to be two different circles and radii, and each one is bigger or smaller than the other one. But they're meeting each other in one point, or they have a tangent or a point of tangency between them. Internally here, when each circle is inside the other one, means internally. When both of them are outside, but they are intersecting in one point, they're meeting in one point, then they are externally tangent circles. Hope this is understood. And now we're going to use these properties or postulates within examples, and you can see here that you are identifying these circles on the grid using the grid lines. So here we're going to say find the length of each radius. Identify. Definitely here I have, for example, this radius for the circle S, or the circle R. Let's start with star R. This is the circle R. We can see that the point here for the circle -2, is here. To the left x, -2. Downward, -2 here. -2, definitely. Left and down, so they're going to meet here in the center. So how much is its radius? Let us, they said, point on the circle and go to its circumference. Distance between this circle and the other circle, we're going to say the green line here, as I draw, it is only 2 steps. So it is its radius. So you can see that the radius here is 2, as I drawn it here. What about the other radius for circle S? It is 1.5. Clearly we can see here that this is here, it's 1.5. Because this is 1 and this is 2. So we can see clearly that we can say clearly that this radius is 1.5, and you can say here it is 1.5 as I mentioned. And here it is 2, definitely. Here it is 1.5. And the center of this circle, definitely it is on the left -2, on the top 1.5. So we can write it in general, saying that this is here, the x part is -2 and the y part is 1.5, and clearly we can see it here. If I may use this, here. Now what about -2, 0? -2, 0 here in the middle, it is the point of tangency between them. So let us read the question again. Find the length of each radius. We have found it. Here for circle S it's 1.5. For circle R it's 2. Identify the point of tangency, and we have identified it. Let us identify it. Here it's in red. We have identified it is, I will use the yellow part. Identify the point of tangency. Okay. So point of tangency is here. This point that's shaded in yellow is the point of tangency. I'm going to write it here, which is -2, 0. You can see from the 0, it's to the left, 2 digits. This is the 0, 2 digits on the left. So this is the point that two circles are touching each other. It means point of tangency, as you can see. Here it is, which is the distance between the 2 circles, definitely. 2 circles. Hope this is understood. Okay. Write the equation of the tangent line finally. Write the equation of the tangent line. At this point. First, you would have to see that these circles. Are these circles touching each other, and the line between them going to be horizontal or vertical? Definitely it's going to be horizontal, like here. So we can see clearly that the x-axis here is the line. Sorry, yes, the x-axis is the line of tangency. So we're gonna say clearly here that y equal to 0. You can see it, students here. You can see it here. Y is equal to 0, but it's not top, it's not bottom. Since it's horizontal, so y equal for all values of zeros, y is for all values of x, all values of x, negatives and 0 and positive for all values of x, y is equal to what? It's 0. So when y is 0, no matter the value of x, this is the line of tangent that passing the point of tangency. Remember that the point of tangency is between them here, and this line is passing it. So this is the tangent. Tangent line. And its equation is y equal to 0, as we can see here. Okay? What's meaning horizontal line is through -2? It means the point of tangency is here, which is, as we mentioned, it is -2, 0, which you can see clearly it is here in this particular area. You can see it here. -2, 0, we said so, -2, 0. By this we have satisfied all the requirements of this question for these two slides. Okay, we have found the radii, the measure of the radii for both. Okay, for each radius, you can see here, find, and then we have found the point of tangency between them, -2, 0. And then we have found the equation, the line of the equation of the tangent, which is y equal to 0 in this slide as well. Hope it's understood. Now let us go for the next example. You can see that we have too many examples that has to be covered. I will not repeat the idea here because it's repeated. Okay, and also here just the line of tangency. I would like just to focus on this. Line of tangency, y equal to -1, as you can see here. And you can see it here. Oh, I'm sorry. You can see it clearly here. And you can see the line of tangency is this. And the point of tangency for this one, you can see it here, which is point of tangency, it's 2, -1. As you can see it here, a certain point of tangency. And we can find the radii, this one and this one. This radius, as you can see, obviously 1, 2, 3. This is 3, and this radius is 1. So this is radius. You can say R1 is equal to 3, and R2 is equal to 1, because the distance is 1, and so on. I think that this example is clear, and you can see that the radius and the radii, this is 3 and this is 1. We have identified on the next slide each one, and that's it. Because it's repeated, that's why I've done it shortly. Now let's take what's the meaning of common tangent. Common tangent is a line that is tangent to two circles. It is a tangent to two circles. So this tangent is touching these two circles where? In these 2 points here and here. And the other tangent is here, and it's touching the two circles where? Here and here. Points of tangency. Lines L and M, as you can see, they are named L and M here, are common external tangents. Why? because they are touching the circles from outside, externally, not between them. So when any line is a tangent to two circles, not between them, it means it's an external tangent. External tangent for both circles, for circle A and circle B. What's the difference with other cases? Yes, here we have these tangents, common tangent. These common tangents P and Q are internally. This is P, this is Q, sorry. Okay, and this is P. Here it's the internal. There, here, and here, external. This is the difference between them. Externally or external tangent. So here we have internal tangent circles, as I have mentioned now. This is internal tangent circles, definitely. And here external tangent circles from outside, as I mentioned, the external tangent circles. Hope it is understood. Now let us take these two theorems, which is the core part of this lesson. It is really the core part of this lesson. I know I have to speed up, yet we have half of the slide, but let us catch up as we have 40 minutes for the lesson. Now, for this, here, in this theorem, if a line is a tangent to a circle, like this red line, if a line is tangent to a circle, then it's perpendicular to the radius drawn to the point tangency. So it means it is perpendicular. Yani 90 degree. Meaning it's 90 degree. It's making 90 degree with the radius. So this 90 degree, it is perpendicular. So if definitely the point of tangency here is B, we have a circle A, and we said if a line L is the tangent to a circle at the point B, then it is perpendicular to the radius of that circle A. It means the radius AB is perpendicular to the line L, making 90 degree between them. There is a meaning of that. Okay, to the point of tangency, as you can see here. Mathematically, how we can express it here? When a line is tangent, it implies. So we can write if it is a tangent to a circle, it implies what? Circle. Sorry for that. It implies what? Perpendicular to the radius. As you can see here. This is the meaning of that. Oppositely, also the theorem 11.1.2, the same meaning. Definitely here in a very short way, it's a very nice. Since we have a line L is perpendicular to the radius AB. Since when L is a tangent. So we can say if L is a tangent perpendicular to AB, so AB is a radius. Okay? This is the condition. Here opposite. If we have perpendicularity happen between the tangent and a line of any circle, then the line here is a tangent. If any line is touching a circle and it is perpendicular to its radius, then this line is a tangent. So we can say that M, let me explain it well. If we have here perpendicularity here, and we have 90 degree as we can see here, this is given, perpendicular, we said, to the radius DC of the circle C, or on the circle C, then the line M is a tangent. So here opposite, when we have perpendicular radius of a circle, this implies tangent, any tangent, or tangent M, for example. And here it is. If we have a line, but we don't know it's a tangent here, this line is M, it's going to be a tangent to the circle in one condition. If it is 90 degree, you can see here, between two brackets, it is perpendicular to the circle. Then it means what? It is a tangent. So here, if a line is perpendicular to a circle, here, on the point of tangency to that circle, then the line is a tangent to that circle, the line M. Okay? And clearly we can see here, it is the line is perpendicular to a radius. It implies what? It implies that the line is a tangent to that circle. By this, hopefully, we have finished our work as was of tangent. However, these two postulates or theorems are clear in a very summary way. Whenever we have a tangent perpendicular to a circle, when you say it's a tangent, then it is perpendicular. When we prove it's a tangent and the point of tangency is there, so 100% is perpendicular to the radius of the point of tangency to that circle. Oppositely, when we have a line perpendicular to that circle at the point of at one point, it means this line is a tangent at the point of tangency to that circle. This is the summary of that. So here we have this example of 4 parts. If we study them early, we can catch up time, definitely. So here we have a flight, Apollo, a spacecraft orbited around the Earth. And what is the distance? Definitely, its altitude is 120 miles. Good. What was the distance from the spacecraft to the Earth horizon rounded to the nearest mile? So here, this is the distance that we are seeing to the Earth, 120 miles. Okay. The number 2 here, part of the example, let's see be the center of the Earth. Definitely, the distance between the center of the Earth and the horizon is fixed. It is 4,000 miles. So the distance, this is fixed. Always it is 4,000 miles. Okay, it means the radius. Wow, it's a radius. And here we have a radius as well. It's also 4,000 miles. What does it mean? It means this EC, all of it, is 4,120 miles. Because from the horizon to the earth, to the ground, it's 120 miles, the airplane. So we have the distance, we want all of that from the center of the earth to the horizon is a radius, it is also 4,000. So the total from the airplane to the center of this is 4,120, which is this one now, which is all of that together, the yellow part. What do they want from us? They want the green part. They want the distance from the airplane. Let me draw an airplane in the fast way. This is the airplane. The distance from the airplane to the horizon. To the horizon where? From the edge, from another point, not the altitude. Because here, this is the altitude. يعني perpendicular. Okay. So, the tangent here, where is the tangent? The tangent to the horizon, it's touching the earth in one point to the horizon. Here we can imagine only distance. We are not touching the earth. But the distance to the edge of the earth is 120. And the fixed distance from the center to the edge of the earth is, the horizon is 4,000. But here, to the edge of the earth, or the horizon from the airplane, we don't know it. So definitely here we're going to use the Pythagorean theorem to calculate. This is how we can imagine the example. Or the spacecraft, because it's orbiting, it is orbiting the ground, or the earth. So when we're going to say, as I mentioned, this is what I've done here, together the altitude here, which is, as we can see, and we know that the from the center of the earth to the horizon is 4,000 only. So we're gonna say, to find here, we're gonna say a square. This is the hypotenuse. So we're gonna say this is, I'm going to the right input. This is the hypotenuse, and this is a side, and this is a side, A and B. Hypotenuse, I'm going to say small c. Here we can say that c square, the c square is equal a square plus b square. And if you turn back here, c square is a square plus b square because it's a right triangle. So ec square equal to eh square plus ch square plus eh square. You can see here, here in this rule, or c square equal to Pythagorean theorem. Who's bigger? The Pythagorean, the hypotenuse, 4,120. One of the sides, which is the altitude, which is the radius from the center to the horizon, is 4,000. But you don't know the distance between the airplane to the edge of the earth, or to the horizon, which is this part, the green part we want to know. As you can see here, the green part we are searching. We're gonna subtract them. The square of them is gonna be 974,400. This is eh square. The square root, to find it, we're gonna square root it, and the square root is 987 miles. This is what? This is 987 miles. Definitely, it's much bigger than the distance between the Earth and the edge of the horizon because altitude. But it is quite enough. Anyhow, it's 9,900, and this is our solution. Hope it is understood. Now to check, we can check saying that a square plus b square is this. Is it equal to c square? Yani if I am squaring this part, the altitude part, and I'm adding the missing part that I found with the 4,000, when I add them, are they equal? No, there's a difference between them. We can see the difference is clearly here. Okay, and this is the difference between the altitude and the non-altitude. The altitude for the airplane and the not altitude. This is the difference. Yeah. This is just to check mentally. Another example, similarly, we can find Kilimanjaro. And here I think we have finished the idea in general. How to use the Pythagorean theorem. You can see that is almost similar, the same example exactly, not more. Finally, I would like to explain this one, even it's taking more than 40 minutes. But I have to explain the theorem because it's the last part of the lesson. No worries. If two segments are tangent to a circle from the same external point, then the segments are congruent. It means if we have a point A, external point, and we have two segments from that point are drawn to a circle, touching the circle in the point B and C, and this is the external point, the green point, then and these lines definitely going to be tangent to the same circle P, so they have to be congruent. They have to be congruent. Two segments to one single circle so they should be congruent. So we can say that AB is congruent to AC. From any point, we can draw another two lines, for example, here. Hopefully. So you can see that they are almost congruent. I cannot use straight line directly, geometric shapes or lines, but almost the same idea. So we can name any names like X and Y and Z, or O and M and N. And we can say that ON is congruent to ON. OM and ON. From any 2 points, and the same, and the same, and the same. It's a rule. And in mathematics, two segments tangent to one circle from the same external point implies what? Implies congruency. Here we can use them definitely. We can say we have HK and HJ here. They are tangent at the point G and K to the circle F, and definitely they are equal. They said they are tangent. The moment they are saying they are tangents, the moment they are saying they are tangents, it means what? They are congruent, using what the theorem saying that two segments tangent to one circle from a certain point. It means they are what? They are congruent. So we are taking this property and implement it here. So they are congruent by these two lines, since they are drawn from one point, which is H. Since they are equal, let us replace HK is 5a minus 32, and HG is 4 plus 2a. They equalize them. We're gonna take definitely 2a to the 5a, this one to the big, and we're gonna take the negative to the positive, negative 30 to the 4. Gonna be 5a minus 2a is 3a, and 2 plus 32, 4 plus 32 is 36. 3 equal to 36 divided by 3, both sides a equal to 12. Since we have found a, let us replace here any one of them. We have replaced in the edgy, and edgy here is 4 plus 2a, 4 plus 2 times 12, 24 plus 4 is 28. And by this here we have proven that this is 28. We can check by the other one. I'll check with you. 5 times 12 is 60. Here 5 times 12 minus 32 is gonna be 60 minus 32. It is equal to 28, which is matching my answer here from both sides, so they are equal. We can say definitely they are equal 100% as they are equal. And by this, we have implemented the last postulate of this lesson, which is tangents. When they draw from an external point to a circle, they are congruent. And we have many examples for this. And here there's a simple quiz for the students. We close the lesson by the quiz, identifying things with them, and we have solved many exercises from the textbook and from the sheets A and B and C according to differentiation. Lower achievers, regular achievers B, sheet B, and high achievers sheet C. This is in every lesson. Have a good day all. Hope it is understood, and to the next lesson, inshallah.